In this screencast, we're going to develop an understanding of an inertial acceleration of point P with respect to point O on a non-circular path, which means that in the polar frame, in our ER and E theta directions, all of these terms are in play. The R double dot minus R theta dot squared in the ER direction, and then in the E theta direction, the 2R dot theta dot plus R theta double dot. When we previously dealt with circular motion, the constraints were that R double dot is equal to 0 and that R dot is equal to 0. And so for this example, we're going to say that neither R dot is equal to 0 or R double dot is equal to 0. And so by having R dot as a positive value, that allows us to have an increasing radius. And we don't necessarily need to have for an increasing radius to have an acceleration in the radial direction, but let's go ahead and assume that that's true. And so our particle P will be speeding up in the radial direction. And so we already have our polar frame applied to our system here, which is the frame B. And let's go ahead and start looking at these different terms. Let's take a look at the ER direction, where we have an R double dot and then minus R theta dot squared. So the R double dot term is going to, if it's positive, will be pointed in this direction, so R double dot in the ER direction. Of course, if it's negative, it would be pointing back toward point O. And then the R theta dot squared is always going to be pointed back toward point O. And we've established that that's the centripetal acceleration. It deals with a change in direction if you're on a circular path. So that's what we're accounting for, is the circularity of the motion in this term in the ER direction. So now let's take a look at our E theta direction. And so we have here two different terms, the 2R dot theta dot plus the R theta double dot. And let's deal with our easy one first, or at least the one that we've already talked about, which is in the E theta direction, we have an R theta double dot term, and this will be pointed in the positive E theta direction if theta dot is positive. It will be in the negative E theta direction if theta double dot is negative. And recall that we called this the tangential acceleration, which is referring to the change in speed of this particle P as it would traverse along a circular path. All right, now we still haven't dealt with this 2R dot theta dot, which is the strangest term out of all of these components. This is called a Coriolis acceleration. And we're going to start out by dealing with this just at face value and then develop some intuition about what this feels like, what this means a little bit later. So looking strictly at this term and its values, we see that the Coriolis acceleration is twice the radial speed multiplied times the rotational speed, theta dot. And it's pointing in the E theta direction. So let's put this in a different color. And so this term is 2R dot theta dot in the E theta direction. Let's apply Newton's second law to it. The left-hand side, just like previous examples, is always based on a free body diagram. And here our free body diagram of particle P has a force F sub r in the ER direction and then F theta in the E theta direction. Now let's insert the values that we take from our free body diagram and our acceleration into Newton's second law. And so solving for the coefficients in each of these directions, we get an F sub r is equal to an m r double dot minus m r theta dot squared, and then an F sub theta is equal to the 2 m r dot theta dot plus m r theta double dot. So tackling the F sub r equation first, this is the force that's in the ER direction, and then we've dealt with the centripetal acceleration before, what's going to keep it on the path. And then what's happening here, this has an opposite sign, it's a positive sign, and so that's going to relax that constraint to allow it to accelerate in the ER direction. And hopefully that's intuitive in just understanding the trade-off between these two terms. And then moving down to the F theta term, let's look at the one that we've already talked about before in a previous screencast, which is the mr theta double dot. And this is what's going to be accelerating or decelerating the particle around the curve. But now we have this extra term to deal with, this 2m r dot theta dot. And so what's interesting here is that this is a coupling of the degrees of freedom where we have an r dot multiplied times the theta dot. Notice that both of these terms are positive for this force F sub theta. And so for the particle to stay on this path, in this trajectory, then we're going to need some additional force in the F theta direction to allow it to stay on that path without a hitch. And so one way to look at each of these four components here is that this r double dot term, mr double dot term, and this mr theta double dot term are acting a lot like equations of motion, because these are our second order ordinary differential equation portions of these. And then these two components here, the minus mr theta dot squared, and then also this Coriolis acceleration, those contributions to the forces here are acting more like constraints when they contribute to the forces on the left-hand side of the equation. In our screencast on circular motion, we went into some substantial detail about this, how this centripetal acceleration contributes to the constraint force. And what we did is we said that if we relax the constraint force in circular motion, then what would happen is we're going to feel a centrifugal force which is pushing us to the outside of the curve. It's a fictitious force, and we would feel that, you know, if we took away the door, took away the seatbelt, we would fly out of the car. But we have that pull on us toward the outside of the radius of the circle. So in a similar way, let's take a look at this Coriolis term here, this 2m r dot theta dot, which is also considered a Coriolis force, and let's put ourselves in a non-inertial reference frame so that we would actually gain some intuition on what this feels like. All right, so let's talk about when you might have experienced this Coriolis force. So let's say that we have a carousel, it's rotating in a counterclockwise direction, and then you're standing about halfway out on the radius. So that means that if you're standing about right here, you're going to be rotating in a circle as the carousel rotates. Now remember that if you're standing still on here, you're still in a non-inertial reference frame because you're rotating around and around the carousel. And so because you're in a non-inertial reference frame and you're standing still, you're still going to feel a force, a fictitious force that's trying to pull you to the outside of the carousel. And remember that we see that here in this term. The Fr is the constraint force, which you have to have that constraint force here, the negative mr theta dot squared, to counteract this fictitious force that you're feeling. And so glancing at the rest of the terms, if we look at the constraint force F theta, then we don't have to deal with this term because we're not moving in and out. With an r dot, that would be 0. And then let's assume that the carousel is going at a constant speed. So theta double dot is equal to 0, so we don't even have to worry about this term. So that's saying that we don't even need a constraint force that's going to be in the e theta direction. All right, so now let's just say you've gotten bored with just standing around at this one spot and you decide to walk to the edge of the carousel. Now, if you've done this before, and I hope that you have, then what's happened as you've tried to move this direction is that you've actually fallen to the right. And the reason this occurred is because of this Coriolis force. This is a fictitious force that's knocking you off balance to the right, and from your perspective in a non-inertial reference frame, it actually feels like there's this imaginary force that's pushing you off to the right. Now, from an inertial reference frame, it just looks like that's what should happen. So let's take a look at this contribution to the F theta, that if it were there, you wouldn't fall, and understand exactly why this is happening to you. So the first thing that we need to consider is that when you were standing still on this carousel, you had a velocity, and it's a tangential velocity to your path. And then as soon as you made a step toward the outside, then you were doing is you were stepping to a point on the carousel that had a larger speed. And so what we see here is that you have an instantaneous change in speed, so you have an acceleration. And so we can see that in a term where we have our mass, and then we have the change in our radius multiplied times theta dot. And so this is where we get the idea that if we change our radius faster, we're going to be changing our speed faster, and then that's going to be one part that contributes to this 2m r dot theta dot term. And so the next piece that we need to look at is that by moving out, we have a change in the radius. And so we have that r dot term, and that r dot term, as the carousel is spinning in this clockwise direction, is changing its direction as well. And it's changing its direction, by this delta theta term. And so we would capture this here as an m, and then we've got our r dot term, and then the time derivative of theta. And so it's these two components where we have stepping to a spot on the carousel which has a higher speed, and then the change in the direction of how we're moving out on that radius that are both contributing to what we call this fictitious force, but this Coriolis force. Now, the inadequacy of being able to establish a constraint is what's actually making us fall, because if we were able to plant our foot and then just have that be very solid, then we wouldn't fall. And so that's why you're able to do that at very slow speeds, because this r dot term is really small, and then you can make that happen. But as you speed up, or if you try to run to the edge of the carousel, or even if you try to run toward the middle of the carousel, that destabilizing fictitious force is going to be that much more. It's going to feel like someone shoved you even harder to make you fall. And so I hope that this example on the carousel moving in and out resonates with you, something that you've done before. If you haven't, I encourage you to go try this out. And this is kind of a small-scale example that we can experience. But the Coriolis force, that fictitious force or Coriolis accelerations, also show up on a much larger scale. And so, for example, if we have the Earth with the North Pole, South Pole here, and we have the Northern Hemisphere and Southern Hemisphere, then it's these Coriolis accelerations which help us understand, why a storm is going to be have a counterclockwise rotation in the Northern Hemisphere and a clockwise rotation in the Southern Hemisphere. Also, the way the toilets flush, in the Northern Hemisphere we have a counterclockwise flush, and then if you were in Australia, for example, or South Africa, you would have a clockwise flush. This is all caused by the rotation of the Earth about the axis that goes through the North and the South Pole. In a similar fashion, in long-range ballistics, you have to account for the Coriolis force, this fictitious force, because the Earth rotates underneath the ballistics. So, in summary, we have some bizarre accelerations that occur due to this Coriolis acceleration. They're always fascinating and interesting in how they affect dynamics in engineering. And from a larger perspective, we've got a great set of tools here in using the polar frame, because we can apply these easily in Newton's second law using our acceleration in this basis, and then also with a little bit of study and practice you can get some great intuition into what each of these terms mean, which allow you to check your problems as you go and understand kinematics of each of your problems in more depth.